Okay, theoretical probability. So we've looked at experimental probability, where you actually complete an experiment and collect the data. Theoretical probability is when you know what the outcome should be and you use that to create your probability. So for example, when tossing a coin, we know the probability of getting heads is 1 out of 2 because you only have 2 options. We haven't actually tossed the coin, we just know the theory behind it. So if it's 1 out of 2, I know from, sorry, I'm having trouble with my recording here. I'm getting caught on things. Let me fix that. All right, let's see if that solves the problem. So where that leaves us then is remembering that we can take our fraction, express it as a decimal, express it as a percent, and they all are the probability of tossing heads when tossing a coin. Probability of rolling a single die, when rolling a single die, sorry, the probability of rolling a 4, we know 4 is one of the numbers out of 6 possible numbers on the dice. So we would have a 1 in 6 chance of rolling a 4. And we could change it to a decimal, we can change it to percent. We know that now. I'm going to leave it as a fraction for this. When drawing a card from a deck of cards, the probability of it being an ace. Well, there's 4 aces in a deck, and there's 52 cards in a deck. So I would have a 4 out of 52 chance of drawing an ace. I could reduce that. They both divide by 4 to a 1 in 13 chance of drawing an ace, or I could change it to a decimal, change it to a percent. If 100 people qualified for a contest where 10 prizes are giving out, the probability of winning a prize, there's 10 prizes and there's 100 people looking for the prize. So you have a 10 in 100 chance. If you reduce that, you'd have a 1 in 10 chance of winning a prize. So theoretical probability we can figure out by using logic and common sense and not actually doing an experiment like experimental probability. Theoretical probability is considered to be the number of successful outcomes, so what we know could happen, divided by the total number of possible outcomes. So to calculate theoretical probability, all outcomes of the experiment must be equally likely. This means that each outcome has the same chance of happening because the conditions are fair. So things that are equally likely are when you flip a coin, or if you draw a card from a deck, or if you pull a name from a hat, or rolling any number of dice. Their outcomes are equally likely to happen, and we can therefore calculate theoretical probability. So for example, if one card is drawn randomly from a standard deck of cards, what is the probability of each event? So probability of drawing a club. There are, if you didn't know, 13 clubs in a deck of cards. That would mean I'd have a chance out of 13 clubs, out of 52 cards, to draw 1 club. And that reduces, they both divide by 13 to a 1 in 4 chance, or you'd have a 25% chance of drawing a club. A jack. There are 4 jacks in a deck of cards. A deck of cards has 52. So we have 4 chances in 52 to draw a jack. And we can reduce that. They both divide by 4 to a 1 in 13 chance. To draw a heart, a club, or a queen. So there would be 13 hearts in a deck, and there would be 13 clubs in a deck, and there'd be 4 queens. But there's already a queen that's a heart and a queen that's a club, so there's only 2 other queens that I could have a possibility of drawing. So 13 plus 13 plus 2 are the cards I have to choose from to get a heart, a club, or a queen out of a total of 52 cards, which means if I add those up, there's 28 possible cards that would fit my outcome out of 52. And I think, yep, that reduces, they both divide by 4 to 7 in a 13 chance of drawing a heart, a club, or a queen. If I want a red card or a king, A red card would be all the hearts, all the diamonds. So there's 13 of each suit. So 13 hearts, 13 diamonds, and there'd be a king in each of those, and then there'd be 2 other cards that would be kings out of 52 cards in total, which is similar to what we just did. Gives me a 28 out of 52 probability, or 7 out of 13. An ace or a face card. So there are 4 jacks, 4 queens, 4 kings, and 4 aces out of the 52 cards. That would mean there's 16 possible outcomes out of a total of 52. And that reduces to a 4 in 13 probability of choosing one of those cards. All right, last one of the cards. A black or a red card. Well, that's the whole deck. So if you had a black or a red card, no matter what you chose, one of those 52 cards would be black or red. So it would be 52 out of 52, or 100% chance, or the probability would be 1. And that's where you can get between 0 and 1 as your probability. If you have something that's a sure thing. All right, dice. Let's look at dice, because that's a good one for probability. If 2 dice are rolled together, what is the probability of the following? To get a sum of 7. So I could roll the first dice, or the first die, and get a 1, and I could roll the second die and get a 6. And I could roll the first die and get a 3, and I could roll the second die and get a 4. Both of those would add up to 7. You see where I'm going with this? I could roll the first die and get a 2, roll the second die and get a 5. But I could also flip it around. I could roll the first die and get a 6, and the second one and get a 1, and the first die and get a 4 and a 3. And you see where I'm going with this, which would mean there would be 1, 2, 3, 4, 5, 6 possible outcomes that would give me a sum of 7. And if I were to roll the dice together, I have 6 numbers on each die. So I'd have 6 times 6 total outcomes, which would give me a total possibility of 36 combinations. So I'd have 6 out of 36 probability, or a 1 in 6 chance of getting a sum of 7. To roll doubles. If I'm going to roll doubles, well, I'd have to have die 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. I got 1, 2, 3, 4, 5, 6 possible outcomes. It's going to give me doubles out of a total combination of 36, which is also a 1 in 6 chance of rolling doubles. To get a sum of 3 or 11, I'm going to make myself a bit of a chart here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Add some of my lines may not. I know I should probably just use my smartboard and make a nice straight line, but I'm just going to freehand it. One more line there. Okay, so I'm going to think of this as my options for die number 1. And these are my options for die number 2. So I could roll a 1, a 2, a 3, a 4, a 5, 6. 1, 2, 3, 4, 5, 6. If I roll a 1 and a 1, they will add up to 2. If I roll a 1 and a 2, they will add up to 3, and so on and so forth across the board. And I'm going to fill in my little table. If I roll a 2 and a 1, well, that will add up to 3. 2 and a 2, 4. And we're maybe starting to see a bit of a pattern here. And I'm going to fill in the rest of the table. Whoops, my mistake. Actually, maybe I'll hit undo. Oh dear. 5, 6, 7, 8, 9. And I keep filling my table. If I roll a 4 and a 1, that will add up to 5. 4 and 2, 6. And I fill in the rest of my table. 5 and 1, 6. 5 and 2, 7. 3, and so on. 6 and 1, 7. 6 and 2. And I figured out all the possible combinations that I could roll and add up the dice to see what I get. So I want, or I'm looking for, a sum of 3 or 11. So I would get 3 here, 3 here, 11 here, and 11 here. Those combinations, if I roll a 2 and a 1, a 1 and a 2, or a 6 and a 5, and a 5 and a 6. That means I have 4 possible outcomes out of a total of 36 outcomes. 2, 6 across, 6 down, all those green numbers are possible outcomes when I roll the 2 dice. So I have 4 out of 36, which would simplify to a 1 in 9 chance of getting a 3, or adding up to 3, or adding up to 11. Okay, so you've got the idea of theoretical probability. You're going to try some questions now with it.